Hey everyone, hope you're having a good day. It was good to see so many of you this morning at Zoom. For those who can't make it or couldn't make it today, I had this YouTube video for you all. I'm learning a lot of things about how to edit videos, how to use Zoom, and I realized today that I have to show what screen I want to record because the recording didn't show the notepad that I was using. So I have to make a new video for you all. For those who didn't see the Zoom meeting this morning, I'm going to go ahead and go over the lesson again right now with you all on my notepad, and hopefully soon I'll get something more high-tech, but for now this is all I have. It's a pretty short lesson and it's just one new concept. So let me go ahead and turn my camera around. Okay, so today we're going to be learning about a mole, and it's not the animal. This is a number. So this number is 6.02 times 10 to the 23rd. So to give it some context, it's just a name for a number, just like we use other names for numbers. A dozen, for example, is a name for 12. A couple is a name for 2. A ream, like a ream of paper, is 500. And so we use mole the same way we use these numbers. So for example, if you were asked, how many eggs do you have if you have 3 dozen eggs? Well, we know there are 12 eggs per dozen. So our unit multiplier would look like this. We want to cross out dozen, so we would put dozen in the denominator. We would put eggs in the numerator, and we want 12 eggs per dozen. Dozen would cancel out. We would do 3 times 12, 36 eggs, and 3 dozen. It's the same conversion if we're going from moles to particles. So if we were to have 3 moles of copper, our conversion would be similar. It's just that instead of using, like we use 12 over 1 dozen here, we know that in 1 mole there are 6.022 times 10 to the 23rd atoms. So we'd see that moles cancel out. We would multiply 3 times 6.022 times 10 to the 23rd, and that would give us how many atoms there were in this copper sample right here. So on the calculator, you might not have ever used a number this big, but what you would need to do to write out 6.022 is you would need to write it as 6.022, but sometimes, students usually will write times 10 caret 23. And it's not really a good habit to get into. It's a lot better to do a different method. So I don't have the TI calculators that you usually use in the classroom, but my calculator has the same button that yours would have too with the TI. So it's the double E button. You can see it right there. So for TIs, it's above the comma. So if you look for the comma button on your TI calculator, you're going to see a double E above the comma. So for me, what I have to do is I have to hit second, and then this button, that'll bring up the E. So if I were to write this in, I would write in 6.022 second E. So you can see on there, it shows up as just 1 E. Even though the button shows 2 E's, you're going to only see 1 E in the calculator. So that's going to be true for yours too. So don't type in 2 E's. You're going to just see 1 E on here, even though you see 2 E's on the button. You'll see 1 E up there. And then 23. So that's how you'd write the number in on your calculator. That will prevent any mistakes that you could make if you wrote it in like this. So write it in as 6.022, hit the double E button once, and then 23. You do not write in 10, you don't write any multiplication, it's just 6.022, the double E button, 23, that's it. That will be the same as this right here. but it cuts down on mistakes. So we would do 3 times that to get the answer. And that would give us 2.11 times 10 to the 24th atoms of copper. So why do we use moles in chemistry? As you can see, we're dealing with very large numbers. So there are a tremendous amount of atoms in a very small amount of space. There are more cups, I'm sorry, actually it's the reverse. If you were to take 1 drop of water, there are more atoms in that drop of water than there are cups of water in the ocean. There are more atoms in that drop of water than there are grains of sand in the whole world. There's more atoms in that drop of water than there are stars in the universe. In that 1 drop of water. So the number of atoms in a very small amount is still tremendous. So moles gives us an easier way to keep count of atoms. Now the person who came up with this idea of a mole was an Italian scientist, Amedeo Avogadro. That's a V. Amedeo Avogadro. In about 1811, he was the one who measured the mole of a gas, 1 mole of gas. He figured out that no matter what kind of gas you had, it was always going to be 22.1 liters of gas to get you 1 mole of gas. I'll talk later about how he discovered that, but this idea of mole was then used in all kinds of forms, not just gas. To give you an idea of how big this number is, if you were to be given Avogadro's number, and so just to clarify, 6.022 times 10 to the 23rd is Avogadro's number. So if we say this is a mole, we can also say it's Avogadro's number. So we use it interchangeably. But this represents 1 mole. If you had Avogadro's number of dollars, and you spend $1 billion every second, it would take you 19 million years to spend all of your money. If you were to give Avogadro's number of pennies to the whole world and distribute it evenly amongst about 8 billion people, everybody would get $1 trillion. If you were to get Avogadro's number of marshmallows, the jumbo-sized marshmallows, and you were to just let them go throughout the world, they would cover the entire Earth 12 miles high. And if you had everybody tried to eat them, everybody ate 1 marshmallow per second, and they just didn't stop. They kept eating until they were all gone. It would take 40 million years for the entire human race to eat all the marshmallows in the world. So hopefully that gives you some perspective. We hear these numbers and it's hard to realize how large they are, but that gives you some idea of how big that number is. I think that covers the basics for today. One more thing before I go. You'll see in your book that they talk about formula units. So a formula unit would be the name for an ionic compound, like NaCl, for example. You have sodium, that's a metal, chlorine, a nonmetal. So anytime you have this compound where you have a metal and nonmetal, you would call that a formula unit. So NaCl would be 1 formula unit. If you were to have 2 NaCls, sorry, I got a frame right there, here we go. So if you had 2 NaCls, what you'd say is I have 2 formula units. So it's just a way to describe this Na bonded to the Cl. If you were to talk about molecules, molecules are names for all non-metals. So if you were to say have H2O, both hydrogen and oxygen are non-metals. So this would be a molecule. So you would say that there's 1 molecule of water if you had 2 of those, we would say now there are 2 water molecules. The other one would be atoms. So, you know, we were looking at compounds that were groups of 2 or more atoms, but you can also have single atoms. You know, helium, for example, is just 1 atom on its own, and so we'd say that that's, you know, just 1 atom. Another helium atom. So these are not bound together. These are separate. So we'd say that this is 2 helium atoms. That's not the same thing as if we were to have, say, H2. H2 is a molecule. So we write it as H with a subscript 2. That represents these atoms have bonded together. So we'd say that this is 1 H2 molecule. Now, we could have 2 H2 molecules. Oh, sorry. Just writing too fast there. So this would be 1, this would be 2. So we would now have 2 H2 molecules. So now, but how many atoms do we have here? We have 2 H2s, but we have 4 H's. We have 4 atoms, but 2 molecules. So that's one thing to keep in mind when you go through the questions today. I think one question in the book, let me check the book really fast. I don't have it with me. Let me get up and find that. Okay, so question 4 says, calculate the number of oxygen atoms in 5 moles of oxygen molecules. Okay, so remember that oxygen is diatomic, so oxygen molecule is O2. That's 1 oxygen molecule. And what they're saying, I cannot write today. There we go. What they're saying is that we have 5 moles of this. Well, before we talk about moles, let's just think about 5 molecules. So let's just say we had 5 O2 molecules. Not moles right now, just molecules. So if we had 5 O2 molecules, what would that look like? Well, it would look like this. So that's 1, you know, we have 2 O's bond together. Okay, so that would be our 5 O2 molecules. So these are 5 molecules, but how many atoms do you have? Well, you have 10 O atoms, but you would have 5 O2 molecules. So that's how you would approach this problem. Now, what are they asking for in the problem? They're asking for how many oxygen atoms are there. So let's think about this before we think about moles. What if we had 5 dozen O2 molecules? If we had 5 dozen O2 molecules, how many O2 atoms would you have? Well, you'd have twice that. You'd have 10 dozen O atoms. Because for every one of these molecules, you have 2 O's, so you would just double this number to get 10. So it's the same concept for moles. What you have is you have 5 moles O2. And just so you know, I'm not being lazy when I do that. Chemists actually drop the E. So if you see me writing MOL, that's the official abbreviation for mole. Okay, so if you have 5 moles of O2, and the question is how many oxygen atoms do you have? Well, again, there's 2 O's for every O2. If you have 5 O2s, we know that we have 10 O's, but we have 5 moles of O2, so we must have 10 moles of oxygen atoms. Alright, so that's the lesson for today. Hopefully that clears it up. And tomorrow at our Zoom meeting at 10, you can ask anything that doesn't make sense in this video. And I think I'll end it there, and I'll see y'all tomorrow.